So far, we've been doing a lot with the augmented matrix, which makes sense because it is a very helpful matrix. However, the augmented matrix is just a special type of partitioned matrix. A partition matrix is just a matrix that's broken into sections or partitions using vertical and horizontal lines. Here's an example of a more complicated partition matrix. This one has 6 different partitions. I've used both vertical and horizontal lines to break up this matrix. We can also write this as what's known as a block matrix, which is this matrix A, B, C, D, E, F, where all 6 of those letters refer to the piece of this matrix. As an example, B would be the submatrix 0, 2, negative 5, 9. E would be the submatrix 3, 10, etc. When dealing with partition matrices, we can add and subtract by adding and subtracting corresponding partitions. We can also multiply partition matrix by a scalar. However, when we work with multiplication, we have to be careful to make sure we preserve order. As an example, here's some matrices that I want to multiply, where I refers to the identity matrix, and 0 refers to the 0 matrix. In order to do this, I need to start by multiplying the first row by the first column. So I have A times C plus I times I. And we know that I times I is just I. For my second column, I have A times I plus I times D, which gives me A plus D. Second row has B times C plus 0 times I, which simplifies to BC. And then finally, B times I plus 0 times D, which just simplifies to B. So you'll notice my first matrix had A and B in it, and my right, all of my multiplication has both A and B on the left, C and D would be on the right. So we do need to make sure we preserve order. Let's look at another one. Here I have a matrix, and I'm going to assume all of these pieces inside the matrix, A, B, C, and 0, are all square. And I want to see if I can find a formula for the inverse. This means I'm looking for formulas for W, X, Y, and Z such that if I multiply my original matrix by the matrix W, X, Y, Z, I should get the identity I0, 0, I. We're going to start by multiplying out the left-hand side. I have A times W plus 0 times Y. That just gives me AW. For the second column, A times X plus 0 times Z. That just gives us AX. Moving to the second row, I have B times W plus C times Y. And then my final entry, B times X plus C times Z. And this still needs to be equal to that identity matrix. So now I have 4 different equations that I can look at and try to solve. The first row gives me AW is equal to I and AX equal to 0. The second row gives me BW plus CY is equal to 0 and BX plus CD is equal to I. I'm going to start with my first one. Invertible matrix theorem says that if a square matrix times another matrix gives the identity, then the inverse exists. So we have W is equal to A inverse. So A is invertible. My second equation, I'm going to go ahead and multiply both sides of this by the inverse. We know that A inverse A is equal to the identity, and the identity times X is equal to X. On the right-hand side, anything times 0 is 0. So now I have that X is equal to 0. And I just realized I had some D's in there that should have been Z's, so go ahead and change those back to Z's. I'm going to use my last equation next. I know that X is equal to 0, so this BX is going to be 0. That tells me that C times Z is equal to I, which means that C has an inverse. In fact, Z is equal to C inverse. So now I have formulas for W, X, and Z. I only have Y left. My third equation, I'm going to stick in what I know for W. That gives me BA inverse plus CY equal to 0. I'll subtract BA inverse over. I'm left with CY equal to negative BA inverse. We've already said that C is invertible, so I can multiply both sides by the inverse of C. And when I do that, the left-hand side becomes Y, the right-hand side becomes negative C inverse BA inverse. So now I have a formula for the inverse of this particular matrix.